Hello everyone, welcome to lab 10. This is the last lab tutorial video for the course. In this lab I'm going to discuss an approach to solve numerically ordinary differential equations with the initial conditions. Let's begin with an example. We have here three first-order differential equations. There are three dependent variables, which are x, y, and z, and one independent variable, which is the time t. And the initial conditions are provided at time t equals to 0. For all the variables, the value is 1. Now our goal is to solve this system of differential equations numerically, and at the end we will plot the solutions. The first step is we need to define the ODES in MATLAB. Here you see I use a MATLAB function handle to define the equations. All the three equations are defined in a single array or matrix, which is F. Also, look at the way the variables are defined. Like y1 refers here to x, y2 is for y, and y3 refers to z. The semicolon here means that the matrix F is a column matrix with 3 rows. Next step, we need to select a numerical approach to solve. For this lab, we will use explicit Euler method. Here I implemented the approach by creating a MATLAB function which is named Explicit Euler. In this function, you see here y refers to our example variables, which are x, y, and z, and x is the time. This is the general form of solution for Euler explicit method, where we seek the solution at t equals ti plus 1 time, which is here represented by yk plus 1. Yk is the initial value, h is the step size, and the f is the function where we defined already the three differential equations with the function handle. The third step and the final step. Actually, you have to call the function Euler function here that we created for solving our ODEs. Here, look at the expressions. Actually, the explicit Euler is the function. I mean, we are calling this function to solve the problem. 0 and 5 is the simulation time periods, and then 1 1 1, these are the initial conditions, and 0.001 is the step size for the solution. Now you need to be careful while define these conditions, initial conditions. For example, I defined the initial condition in a column vector with the semicolon here because the Euler function I defined, the left side has a dimension of 3 by 1, so the right side has to have the same matrix dimensions. We can also plot our results to see how the solution evolves with time. The simple plotting technique we have implemented here to represent the solutions for the three variables x, y, z for a step size of 0.001. The previous example shows the first order ODEs. Now we may have second or higher order ODEs that we can transform them into a system of first order ODEs. For example, here we have two second order ODEs. We can assume that dx by dt equals to EU and dy dt equals to V. Now if we differentiate that, so it becomes dx square over dt square is du dt, and dv dt refers to the second derivative of y with respect to t. Now after defining this two, first derivative and second derivative, now if we substitute this into these two equations, so we can write it in this form. So now what happens actually? Actually we can substitute these two equations by four first order differential equations, where u equals to dx dt, the first derivative we have already assumed, v is the first derivative for another equation, y, the variable is y. So and these two equations, actually second order, if you consider u, which is a derivative of first order, but by writing all these four equations are first order, so we can handle any order of equations and make it a system of first order differential equations for our convenience and to solve the problems. In your assignment problem, you are required to implement the explicit Euler method to solve ODEs. But there are a few additional things to discuss. There is a question where it asks you to estimate the distance traveled by the rock when it hits the ground. For that, just think of a condition to establish the point when the rock first hits the ground, and after that try to estimate a value of horizontal distance x in which the condition is satisfied. The next question, how can we find the maximum horizontal distance that is traveled by the rock? To do that, you need to rerun your simulations for different starting angles. It may involve several repeated simulations where you may consider the longest magnitude. In your assignment in question 2, you'll be asked to find optimal angle for the maximum distance traveled. For that, you may use several loops to find the distance at different angles. This approach is called local refinement. Here we will find maximum distances from these angles and then find two intervals close to that point of interest and recalculate the distance. This operation should be continued until the change between 2 points is minimal, such as below 10 to the power minus 3, 10 to the power minus 4, and so on. There is also a question which asks you to explain the reason for the angle theta max not being 45 degree for the maximum distance traveled by the rock. For this to understand, you need to plot the rock trajectory at different angles. So for example, at low angle, medium angle, or high angles, and then observe the results. You may also compare the velocity vectors along the trajectory between two angles, say the angle 45 degree and your optimal angle. You may use MATLAB commands feather, which will make this comparison step a little bit easier.